this video, I am going to derive the conduction heat transfer differential equation. And for that, let's assume that we have a system with a control volume and control surface. Let's assume that this is our system. The control volume and control surface. So the first step, we are going to write the conservation of energy equation for this system. Conservation of energy states that the rate of increase within the internal energy of a system is equal to the energy that leaves the system plus the energy that is generated within the system and plus the work done on the system. So let's write that thing down. So rate of increase in internal energy of the control volume of the system, the control volume is equal to the energy that transfer from the system plus the energy that is generated within the system plus the energy that is generated within the system plus the work done on a system So the rate of increase in internal energy of a system is equal to the energy that transfers from the system plus the energy that is generated within the system plus the work done on a system. Now, since we want to go ahead and derive the differential equation for conduction heat transfer, our first assumption is our system is solid. The conduction heat transfer means heat transfer within solid. So our first assumption is our system is solid. So since our system is solid and it's not a fluid, it's not a gas, so this portion of the energy equation will be 0. Our second assumption, our system is stationary. It's a solid, stationary, it's not moving, so there is no velocity. And then our system is homogeneous. And we are going to restrict ourselves to the isotropic materials. So it's isotropic material, and we have some sort of internal energy generation, and let's show that internal energy generation by U dot prime prime prime. So these are our assumptions. So by using these assumptions, let's go ahead and translate this statement into a formula. So for the first portion, rate of increase in internal energy of our control volume, let's let's assume a small differential volume and be showed by the dV. And let's write the rate of increase of energy within that differential volume. So the rate of increase, the internal energy of a differential volume, we can write it as rho dV. Rho dV is the mass. Mass by definition is density multiplied by volume. So the mass of that differential volume will be rho dV. So the internal energy of that unit mass, we can show it as mass multiplied by U, the internal energy U, plus half V squared. So this is the internal energy within that differential volume. And since we have assumed that our system is stationary, low velocity, so this portion will be 0. So our mass, our energy within that differential volume, we can write it as rho u dV. Which is mass multiplied by U. Now, rate of increase. So we can show the rate of increase by partial derivative with respect to time. So this is the rate of increase of energy within this differential volume. So for us to find out for the entire volume of our system, we have to take the integration over the entire volume of our system. So this first portion, so far, we are at this point. Now, if we look at the thermodynamic law, we can write in terms of du is equal to, let's first write this as, we can write this as rho partial derivative of u with respect to time dv. Now, the thermodynamic law states that du is equal to Cp dt. This Cp is the constant pressure dt and T is temperature. And since we are solid, so in solid Cv is equal to Cp. So here, partial derivative of u, we can write it as Cp partial derivative of T, time. So let's go ahead and plug that in here. So we can write this equation as, we can write this portion as control volume rho, instead of partial derivative of u, we can write this. So we can put this as rho Cp partial derivative of temperature with respect to time. dV. So if we plug this value in here, we get this. So this is our first portion of this equation. Now the second portion, energy that transferred from the system. The energy that leaves the system will be in the form of heat. So for this portion, let's assume a differential surface, and let's show this differential surface by the vector ds. And let's assume that the heat is leaving that differential surface in this direction. And we show the heat by Q, vector Q. So the heat that leaves that differential surface, we can write it as minus Q dot ds. Why minus? Because the energy is leaving the system, so there will be a decrease in energy in our system. So that's why this minus is for. Now this is the heat transfer from that differential surface. So in order for us to find out the heat transfer from the entire surface of our system, we have to take the integration over the entire surface of our system. So this is equal to, so this is that portion of our statement. Plus the energy that is generated within the system. Let's assume that we say that we are going to show it by U dot prime prime prime. So this U dV. So let's assume that this is the internal, this is the energy generated within that differential volume. So for the entire volume of our system, we have to take the integration over the entire volume. So this is, we don't need this. So now we have translated this statement into a formula. Here we have an integral formula with three integrals, and two of them are volume integrals, one is surface integral. Now again, here, like we did in continuity equation, we use the Gauss divergence term, and we transfer this integral into a volume integral. So the Gauss divergence theorem states that if we have a surface integral of let's say like this, if we have the surface integral of Q dot ds, this is equal to the volume integral of del dot Q dV. So now we can use this theorem and transfer this control surface integral into a controlled volume integral. So we can write this equation as rho Cp partial derivative of t with respect to time dv equal to minus, and this we can write it as del dot q dv plus control, so this is over control volume, and u dv. So now all our integrals are volume integrals, so we can solve this equation. So in order for us to solve this, let's go ahead and rewrite this equation as we are bringing those to the left side and factoring out the integral, so we can write it as rho Cp partial derivative of t with respect to time plus del dot q plus minus. This was minus, comes to the left, become positive. That's plus, comes to the left, become negative. dv equal to 0. So what we did, we brought everything to the left side of the equation. Now, in order for us to reach here, we assume the system with the control volume and control surface. So because of that, our integral cannot be equal to 0. So the only way that this equation can be 0 is if this portion of the equation is 0. So if rho Cp partial derivative of t with respect to time plus del dot q minus equal to 0. Now here, this Q, the heat transfer, according to the Fourier-Biot law, the Fourier-Biot law states that heat transfer Q is equal to minus K Ij partial derivative of temperature with respect to x Ij. So since we are, one of our assumptions was also restricting ourselves to the isotropic material, so Kij will be equal to 0 when I is different than J. And Kij will be equal to K which K is the thermal conductivity. K is the thermal conductivity. Each metal have a different thermal conductivity. That's shown by K. So Kij will be equal to K when I is equal to J. So we can write this Fourier-Bayet law in a general form for the isotropic material as Q is equal to minus K partial derivative of T with respect to Xi. Qi is equal to minus K with respect to Xi. So that means that Q in X direction is equal to minus K partial derivative of T with respect to X direction, and Q in Y direction is minus K partial derivative of T with respect to Y direction, and Q in Z direction is minus K partial derivative of T with respect to Z direction. So let's write it in a vector form. In a vector form, we can write this Q vector is equal to minus K del T. So in a vector form, we can write it in this form. So let's go ahead and plot that value for the Q in this equation right here. So we are going to have rho Cp partial derivative of time with respect to T plus, okay, let's go ahead, before that, let's go ahead and rewrite this equation again like we had before. We write it as rho Cp partial derivative of T with respect to time is equal to minus del dot Q plus U prime prime prime. Let's write it like this. We bring this to the right side of the equation. Now let's put that value for the Q in here. So we are going to have rho Cp partial derivative of T with respect to time equal to minus del dot Q. Our Q is minus K del T plus okay, what we did, we rewrote that like beginning, and we replaced this Q by minus K del T. Now this is our this is our conduction, heat transfer, differential equation. This is our conduction heat transfer differential equation. Now, let's look at some special cases. Okay, let's say case number 1. Our thermal conductivity K is uniform. So case number 5, we have uniform thermal conductivity. So in this case, we can write our equation as rho Cp partial derivative of time with respect to t is equal to minus times minus is plus k. After we do the dot product, we are going to have del square t plus this. So if our thermal conductivity is uniform, we can write this equation like that. And let's go ahead and divide both sides of the equation by k. So on left side, we are going to have rho Cp divided by k, partial derivative of time with respect to partial derivative of temperature with respect to time is equal to k divided by k is 1 is equal to del square t plus u dot divided by k. We divide both sides of the equation by k. This k divided by rho Cp it is called alpha, which is called thermal diffusivity. Thermal diffusivity. By definition, the thermal diffusivity is equal to the thermal conductivity divided by density multiplied by the constant pressure. So we can write, using that we can write this, since this is the inverse, so we can write this as 1 over alpha partial derivative of t with respect to time is equal to del square t plus divided by k. Now the case number 2, let's assume again that we have uniform K with no internal heat generation. So if we have no internal heat generation, that means this portion will be equal to 0 with no internal heat generation. So in this case, our equation will be 1 over alpha partial derivative of temperature with respect to time equal to minus del square T equal to 0. So this is called the diffusion equation. So this is the diffusion differential equation. Now, let's look at case number 3. We have uniform K, uniform thermal conductivity, a steady state, what the steady state means there is no change with respect to time. So if we have uniform K with a steady state, so this portion will be 0, so our equation will be del square T plus U dot divided by K equal to 0. So this is for case number 3, uniform K, steady state, no change with respect to time. This equation is called the Poisson's equation. And the last case, let's look at uniform K, a steady state, and no internal heat generation, or energy generation. So in this case, uniform K, so this will be our equation, a steady state, this portion will be 0, and no internal heat generation, this portion will be 0. So in that case, this will be 0, and this will be 0. So we are going to have del square equal to 0. So this is called Laplace equation. And now we have the conduction heat transfer differential equation, and using this equation we applied these cases and we drove the diffusion equation, Poisson's equation, and Laplace equation. Now we can write, by knowing this value for the del, we can write this equation in Cartesian, cylindrical, and spherical coordinates. So just before I start this video, I went on Google and searched for del operator. So and I wrote the values of del operators. So by using these del operators in different coordinate systems, we can write these equations in different coordinate systems. So I am going to write those that I got online for del operator. So what we really need is this del square. So del square in Cartesian coordinate system is so this is del squared in Cartesian coordinate system. So we can apply that in these formulas and write these formulas using that in Cartesian coordinate system. If we need it in cylindrical coordinate system, del square in cylindrical coordinate system is partial square with respect to r square plus 1 over r partial with respect to r plus 1 over r square partial square with respect to theta square, and in cylindrical square we know that our z-axis stays the same, plus with respect to z square. So we can use this and write our equation in cylindrical equation, and if we ever need, I never have needed it, but if we ever needed to write it in a spherical coordinate system, this is the del square in a spherical coordinate system. Is 1 over r square partial derivative with respect to r square partial with respect to r plus 1 over r square sine of theta partial derivative with respect to theta multiplied by sine of theta partial derivative with respect to theta plus 1 over r square sine square of theta partial square with respect to phi square. And this is a del squared in spherical coordinates. So we can use these values for del squared and write our equations in all coordinate systems.